It is my privilege to introduce Professor Rakesh Kumar Singh ji. Professor Rakesh Kumar Singh is an accomplished scientist and educator, currently serving as an associate professor in the Department of Physics at the Indian Institute of Technology, BHU, India. He completed his master's degree at BHU and earned his PhD from the Indian Institute of Technology, Delhi. Throughout his academic and research career, Professor Singh has gained extensive international experience. He has served as a JSPS fellow at the University of Electrocommunication in Tokyo, Japan. Additionally, he has held position as a postdoctoral researcher at the University of Oulu in Finland and as a visiting researcher at a prestigious institutions such as the National University of Ireland, Denmark Technical University, Tel Aviv University, Bar Ilan University, Israel, etc. Professor Singh's research is centered around the domain of optics and photonics, encompassing various aspects such as optical imaging, biomedical optics, optical metrology, coherence optics, digital holography, etc. His work is marked by a deep commitment to advancing the understanding and application of light and its interaction with matter. In recognition of his contribution to the field, Professor Singh holds the status of a senior member in respected organizations like SPI, Society of Photo Optical Instrumentation Engineers, Optica, and is also life member of the Optical Society of India. He has more than 160 journals and conference papers and a patent to his credit. On behalf of all RIOS members, I welcome you, Professor Rakesh Kumar Singh ji, to this webinar, and I also welcome all the invited guests and participants to the webinar. Now I kindly request Professor Rakesh Kumar Singh ji to begin the presentation.
Thank you very much. It's an honor to again connect with Kerala University and particularly your department. I have visited many times your department, so it's a great honor for me. In this talk, my objective is to explain the very fundamental of holography and then explain what are the emerging trends in the holography, particularly doing holography with classical and quantum sources. Some of our recent works in this domain, and what are the future opportunities and which direction this particular holography research is going on. So I will try to cover these topics within a given time slot. So I come from already explained, I come from the Department of Physics, IIT BHU. Prior to joining this department, I was in Trivandrum. I worked for around 6 years in IST Trivandrum. So some of the works which I will share in this presentation is from one of my former students who did master from the Kerala University. So I will share one of his works. Okay. So this is the outline of my talk. Basically, in the beginning, I will try to cover the very fundamental features of the light, particularly the correlation, and how do we measure the correlations, and what are the different methods to characterize the correlation features of the light. Particularly, I will initiate discussion on the first order interferometer. And then I will go to the higher order interferometers, which are very unique in terms of giving some unknown features of the light, which may not be possible with a lower order interferometer. So in the beginning, I will discuss the light and interference, and we know the interference is a very fundamental. It gives a very fundamental features of the light, and then we will discuss initially the first order interferometer and then connect with holography. Why holography? Because holography provides the complete wavefront information and very useful in the visual domain where directly measuring the phase of the light is very difficult. So we'll discuss the quantitative imaging using the holography, and then try to connect. I try to extend the holography beyond the first order interferometer, or what we usually call it the Young's approach, or the field-based interferometer. So I will discuss some of the application of the holography and the field-based interferometer, and then some of the existing challenges in the holography and how we can go beyond how we can extend the holography to the higher order. Particularly a technique called the Henry Brown twist interferometer, And then we'll discuss the Henry-Varanasi approach with quantum and classical light. And then finally, we'll discuss some of our contributions on the ghost diffraction holography and then single pixel. And then I will conclude my talk. Okay, so when we consider the light, in general, light may have the fluctuating characteristic. So the question is how to characterize the light. So we need to measure for the characterization purpose. We need to measure several fundamental features of the light, and one of the fundamental features is the correlation. So in order to characterize this kind of light, fluctuating light, we need to measure its correlation. Apart from correlation, our interest is also to tailor the fluctuating light. Particularly in some of the imaging applications, we need tailored correlation of the light. For example, in the tomography or imaging through the scattering medium, we need light sources with very controlled or predefined correlation structures. So we are also working on the tailoring the coherence and polarization of the light. But in this talk, I will mainly concentrate on the analysis of the correlations, 2-point correlations, using different kind of interferometers, first order and second order interferometers. However, I'll be happy to take the question if anybody is interested to know what are the emerging interests into the tailoring the coherence of the light, because this area is emerging very fast because of interest in optical communication and then imaging through the scattering medium. However, to just align with the title of my presentation, I will concentrate mainly on the analysis of the correlation. Okay. So when we consider the light source, let me so explain the the fundamental features of the light, what we call the 2-point correlations. So if you consider the 2-point correlation, usually I'm considering here the quasi-monochromatic source. So in this case, the correlation is explained here. The spatial correlation is explained here as a function of 2 points, R1 and R2. And this is represented by this, the delta function, because I'm considering the monochromatic light source. And then there is the intensity variation, which is considered to be the slowly varying function in comparison to the coherence function mu. The coherence function is is a function of the two position coordinates R2 and R1. So the first term is a spectrum, second term represents the slowly varying intensity distribution, and the third term represents the fast varying the coherence function. And in order to quantify the statistical properties of the light, we need to measure this quantity. So one of the very famous experiments, or one of the very famous approach to characterize the correlation properties of the light is based on the Young's interference experiment. So for example, if I consider the light coming from these two sources and allow these two light to propagate and interfere at the observation plane here, so using the fringe visibility, we can characterize the degree of coherence of the source, and usually the modulus part of the degree of coherence. Please remember, the coherence is usually the complex quantity because it's a 2-point quantity and follows the wave equation similar like optical field. So it's a complex quantity. However, in some of the experiments, only amplitude information is availability of an amplitude information of the coherence function is else. If you are only interested in characterizing the light, but if you want to go beyond the characterization and you want to develop or you want to utilize the coherence function in the imaging, you also need to measure the phase. So mu is having both amplitude and phase. However, in the context of only characterizing or analysis of the light source, amplitude of the mu is enough. Now, so based on the correlations or based on interference, we can determine several local and non-local properties, or we can connect several local and non-local properties of the light. Some of the local properties are listed here, like intensity, polarization, and flux. Please remember, if you want to extend the coherence theory to the polarization domain, it's a little bit complicated, because when we consider the coherence, usually in the textbook, unless it is specified, usually you discuss only with the interference fringe visibility. But if you want to consider the light source, which is non-uniformly polarized, having the polarization fluctuation in the light itself, then in that case you need to extend the theory of coherence in such a way that it also accommodates the polarization in a common framework. And that particular subject has triggered a lot of discussion and interest after the pioneering work of the Professor Emil Wolf. For his student, I suggest that you can go through his book, The Unified, and particularly on the unified theory of coherence and polarization. So a lot of discussion, a lot of interest are coming where people are trying to accommodate and coherence and polarization in a common framework. But in this talk, my main interest, I will not discuss the polarization part. I am ignoring. I will consider only I'm going only to the scalar domain. The polarization part is ignored. However, if anybody is interested to discuss on how to extend the this particular area to the polarization domain, I will be happy to answer. Okay. So if I consider the interference of the light at the interference plane, the interference fringe will be modulated by, it will have mainly the three components. First two terms are very, is like a non-modulating term. However, the third term is a modulating term, which carries the information of the source coherence. And since I'm not discussing the polarization, so I'm ignoring this part, P part. I'm mainly concentrating on the correlation. So the correlation, if you see here, so correlation at 2 points, so the source is represented by this degree of coherence. So the interferometer, which I described previously, this is the first order interferometer because it's working on the basis of correlation between the complex electric field or the complex field. So this kind of interferometer, we call it a first order interferometer. Now, one of the applications of this, there are plenty of applications of the this interferometer. However, I'm in this talk, I will discuss mainly the holography and its relation with the first order interferometer. So the major problem in the optics is to preserve the phase information of the light. And for that purpose, holography is one of the methods, very popular methods to preserve and reconstruct the complex field. So based on the first order interferometer. So it's a basic principle of the holography is just represented here using a two-step process recording. So if I suppose you have the object which is having the complex field represented by O, and if you allow this light to interfere with a reference, and so this, with the help of the reference, we are able to record the interference fringes here. So hologram, at this plane, we record the interference fringes. Now, this interference fringes is represented by R plus O modulus square because it's the field-based interferometer, and like what I explained previously, and what the interferogram will have this kind of term. The first two terms will be non-modulating, unmodulated term, and the third term is modulating term, which carries the information of object O and its phase. Now, the second process in the holography is the reconstruction. So, if you allow the recorded hologram, and this talk I'm mainly concentrating on the what we call the digital holography. So, if I digitally reconstruct this kind of hologram, so what I get, if I digitally reconstruct, I get the virtual image and also the real image of the object. So see here, this will get the two copies because this term is having this term is having the two copies because of this sign function. So one is a virtual copy and other is a real copy. Now, so this is a reconstruction process, and because of this, this issue is because here we get the two copies, and these two copies are coming because of the particular nature of the interference pattern. So as we noticed here that in previous case that with the help of the interferometry, we are able to preserve and reconstruct the complex field of the light. So the first idea, means the idea on the holography was proposed long back by Professor Dennis Geber, where he gave a very simple idea to record and reconstruct the complex field, but it was proposed in a different, not in the optics, but in a different domain. However, after the invention of after the availability of the laser, the holography became a very popular technique, particularly in the optics. So so one of the steps, one of the methods involved in the digital holography is represented here, is recording and the reconstruction. So once you have the recorded hologram in the digital, because this I'm discussing mainly the digital holography. So you take this hologram to the computer, because the data what you record in here, you get to the CCD or your CMOS camera, and then you take this data on your computer and then digitally process. Once you digitally process, you get the, for example, here I use the vortex beam, I got the amplitude and then phase. But however, if you remove this reference beam, you will never get the phase structure. So beauty of the holography is that it is able to preserve the phase information of the light, which was not possible without the reference. So this is the first. Geber gave the inline holography concept, which is a very simple holographic setup, and it's also called the inline holography setup, where you illuminate your object with a collimated beam, and then you get the interference of the diffracted and diffracted beam, and then once you have the recorded hologram, you reconstruct it. However, the major problem in this kind of holography is the inline problem, because a twin image, virtual and the real, both are in the same line of sight, and this is one of the this is the main problem in the inline holography. Another concept, another idea or another geometry was proposed. It's called off-axis holography by Lee Thinopatnik, where the idea is to allow the two interfering beams coming at different angle. So you give certain angle, and then with the help of this angular separation, once you reconstruct this hologram, now the virtual and real images will be separated, and that helps to remove the twin image problem. However, the problem in the digital holography is the stability. In order to overcome some of the stabilities problem in the digital holography, we propose a very simple concept, what we call the radial sharing interferometer in cyclic geometry. And what we did, we put the object here in the half part of the beam, and other part of the beam was just without any object, and then we did the sharing. Using this approach, we are able to we recovered this object. You can put any kind of complex object here. We use the higher order vortex beam, and then you see the reconstruction of the experimental reconstruction of the complex field. Here is amplitude and phase. Apart from the quantitative imaging, like shown here, quantitative phase imaging, this experimental setup is also highly stable. So what we did, we put the vibrating mobile near to the experimental setup, and you see the results. Almost you get the same stability like without mobile, like if you just put the experiment in the highly vibrating condition, with a stable vibration isolation table shown here in the red color, and this with in the presence of mobile, and we had almost same result. So this experimental setup was very effective. Now, so holography is having several applications. However, in this talk, I will discuss applications related only to the holographic microscope, particularly for the in the biology. So why holographic microscope is important? Because it gives you the quantitative phase information, which is not possible in other kind of microscope. It's different from qualitative, like Germanic phase contrast microscope, or we can also extend this idea of holographic microscope to the polarization domain. And it's a level-free imaging. There is no need to tag your sample. And then I'll share some of our recent results in this domain. So, so you can use this kind of microscope, holographic microscope, for real live imaging without any tagging. And here I am sharing the results from one of the very famous company called TomoQ, where they have the product based on the holographic microscope. So see their results. So you can use this kind of microscope for the level-free imaging. Very recently, what we have done, we have extended the concept of holography to the polarization domain. So here I will share one of our results where we use the polarization microscope for the live cell cancer imaging. So the idea is that we have this coherent light, and it's again the first order interferometer, which I explained earlier. So it's a magenta interferometer based with coherent light. So one part of the beam is going to the reference arm. And the reference arm, we use the multiplexing. For the multiplexing, we give angular tilt to the different orthogonal polarization component. So two orthogonally polarized components having different frequencies, they are coming from the reference arm. This is the reference arm. The light coming from the object is coming from this side, and you see here this sample, and then we have the microscope imaging system, 4F system, and then this imaging system translates the information of the object from sample to the camera. Now this object information is being interfered with the light coming from this arm, and we have the polarization interferogram. Now please remember, this is a polarization interferogram. This is different from hologram which I referred earlier. Now, because this polarization hologram captures both orthogonal polarization component of the light from only one measurement. So we are able to preserve the two orthogonal bases, X and Y, of the light into the one polarization component, into only one hologram recording, and then we are able to reconstruct the amplitude and phase of the orthogonal component. So this is a single hologram of a cell, and once we digitally, because this is a digital holography, so once we have the hologram in computer, take the digitally process the data, and we got the amplitude and phase. So this is the image of the cancer cell. It's a U87mg, and we were able to recover its anisotropy. So these are some key benefits of the holography, like no leveling, low phototoxicity, fast imaging, high resolution, and quantitative features. However, there are, apart from many unique features, there are several limitations of the holography. Some of the limitations are listed here, particularly the speckle noise. If you are doing holography with a coherent light and your sample is not smooth, particularly the metallic sample, you see here I have used here the metal, it's a coin with a blade. So in that case, the coherent light is not good choice. And another issue is that you need highly stable setup, distortion due to the aberrations in the path of the light, and then complicated experimental geometry. And some of these limitations, they appear because of the first order interferometer. So what is possible solution? Possible solution is to take this holography beyond the first order interferometer. So we are working in this domain. So here I'm explaining how to use the different higher order interferometer, and one example is what we call the second order interferometer. Suppose the light is coming from, this is a fluctuating light, and this is a light source you want to characterize. One of the possible options is that you do the correlation of the intensity rather than measuring the average intensity. Rather than measuring IF in sample average, you do the measurement of I1, I2 in sample average. And that helps you to overcome certain limitations of the holography, which I explained earlier. This correlation, particularly the second order interferometer, is also called the Henry-Brown-Twist interferometer, and this idea was initially proposed in the particularly in the radio astronomy for different regions. So, but after that, it is extended to a different domains, including the holography and imaging. So I will try to briefly cover the way the history of this interferometer and then explain how it's related to the holography with the classical and quantum sources, and also to the quantum imaging. So if I consider the light coming from, suppose this is a light and you want to characterize using the intensity interferometer. So what you do, you detect the intensity at the you get two detectors and then measure the coincident count. So this coincident count normalized value is represented by this, and this kind of interferometer is highly stable. So the idea of the HBT approach was proposed initially to measure the size of the star, size of the incoherent object, and how it works. So let me explain it. So if you have the incoherent source, so light coming from the incoherent source is being detected by two detectors. So what these two detectors, intensity correlation of these two detectors will give you the modulus square of the coherence function. And this coherence function W is nothing but the Fourier transform of the source. So what you get, the intensity correlation will give this quantity. And if you take again the Fourier transform of this quantity, because if you take the Fourier transform of modulus square, it will be convolution, it will be product of convolution of the product of two functions. So because convolution will give using the size of the convolution, you can estimate what is the source structure. And this idea was utilized to measure the size of the incoherent object. However, apart from the measuring the size, since my interest is in imaging, not only the measuring what is the target and what is the size of the incoherent object, my interest is in the imaging. Apart from size, I also want to see what are the spatial features within the target. So for that purpose, we need a complex quantity W, not only modulus square. So I will explain how we recovered the W. Okay, and so apart from some experiments in astronomy and other domain, the HBT experiment, HBT idea also triggered a lot of discussion on the two-photon imaging or two-photon interferometry. And one of the emerging interests nowadays in the quantum imaging. So where people are exploring quantum imaging, or what they also call the quantum inspired imaging, where their idea is to use the resource or use the basis of the quantum optics and then apply utilize the available and advanced classical resources to mimic or to experimentally test some of the ideas proposed in the quantum domain. So, and one of such initiatives is in the what we call the ghost imaging and ghost affection. So here, the quantum imaging in this, for example, if we consider the quantum source, and if you take the paired photon, one is in the this part H1 represented by the propagation H1 and then H2, and then measure the coincident counting. Similar experiments you can also design with a classical source, or what we call the thermal light source, where you can split the light into two parts and then you measure the correlation. So this kind of experiments, this kind of interest has created a lot of new ideas and new initiatives, particularly measuring the non-local correlation. So for example, if you see here, this is what we call the if you have here you have the quantum source, and then the one photon is propagating, moving in this arm where you is interacting with a target, and then if you collect this light coming from this arm with a detector, a bucket detector, so you will get nothing. You will not be able to see the object. On the other hand, if you take the light from another arm, which is not interacting photon with another arm, which is not interacting with the object. And if you measure with a camera, you will get nothing. However, if you do correlate this light, if you do the coefficient counting of the from these two arms, then you are able to recover the target or the object. And this kind of particularly this unique features has created a lot of interest among in the optics and photonics community, where people are trying to explore the imaging with the quantum and classical sources. So the similar kind of experiment, a similar test, one can also do with a classical source. And this is a very beautiful review paper. You can find out the detailed discussion on the quantum imaging, particularly the ghost imaging with quantum and classical and computational sources. So I will also try to explain what is a computational source here. So for example, if you consider the source here, like I explained previously, one part of the beam is coming to this arm with you have the bucket detector, light coming after the interacting with object, and then another copy which goes directly and interfere being detected by the what we call the array detector, and then you correlate, and the correlation will give the information of the object. Now one can also replace this kind of light source by digital source using the spatial light modulator and do the imaging. And that kind of technique is called computational ghost imaging or computational ghost diffraction. Okay. So because of the certain analogy and certain common features, people are exploring the two-photon imaging with the classical sources. So like I explained previously, for the quantum source, here you can also do you can do the experiment with a classical source with like a thermal light source. So see here exactly similar features. One part of the beam is going to the array detector without interacting with the object, and another copy which interacts with the object goes to the this arm. And then you measure the correlation, and that correlation will provide the information of the object. So if you try to connect or if you try to find out the common analogy, there are certain features which guides us to explore this quantum inspired imaging, or what we call the replacing the possibility of replacing the quantum source with the classical source and explore certain unique features in the imaging. So the common links are, some of the common links are mentioned here. So classical optics, you have the complex field. Here you have the two-photon probability, amplitude, intensity, and here you have the coincident count. And this relation, particularly this relation, is called the length equation for the quantum source. So what we have noticed that if we try to take advantage of the higher order interferometers, here I'm discussing only the second order interferometer, but one can also go to beyond the second order interferometer and develop some of the unique imaging systems, which will be free from the randomness or effect of the atmospheric turbulence or aberration, etc. However, there are certain costs, particularly related to the computation. So, so what presently we are doing, we are trying to recover the information which is hidden in the random light using the second order interferometer. So we can follow we can apply the second order interferometer either using the intensity like conventional HBT experiment, and in parallel we can also extend this kind of interferometer to the polarization domain like Stokes parameters. So these are these are our recent works where we have extended the intensity correlation, second order intensity correlation, to the Stokes correlation, and we have recovered many some unique features of the target which is not possible using the conventional HBT experiment. So I will try to cover some of these results in the presentation. Okay. If you see the ghost imaging, so So the idea of the ghost imaging is that you take here the source, which is maybe the quantum source or the classical source. You split into two parts. One part will interact with objects. So this part is interacting with object, and another part is just going to the detector. Sorry, this is a detector, array detector. So one part is going from the source. Here is the thermal light source. From source is going to the target and then being reflected and coming to the single pixel detector. Another part which being reflected from the source goes to the array detector. So now we have the light at the array detector and the single pixel detector, and then you correlate. So this correlation is because it's the intensity correlation. So you see here, one part of the light is only interacting with object. Other part which comes directly is not interacting with object. However, if you correlate these two lights, like I explained previously, we are able to get the modulus of the Fourier spectrum of the object. So, however, my interest is not only the modulus. I want to preserve. I want to get the f, not modulus square of f. So, in order to recover this f, what we did, we utilize this complex. We utilize this quantity modulus square and put into an algorithm what we call the FINF type algorithm. It's an iterative algorithm which recovers from the modulus square of this quantity, modulus square of the Fourier spectrum, which is represented here. You see here, f is nothing but a Fourier transform. Ft is a Fourier transform of the incoherent source. So using this technique, we are able to recover the phase. And you see here, so my target was a circle, annular ring, and we are using this correlation ghost imaging technique. We were able to recover this target. This is the original target, and this is experimental result. This is the original slit, and this is experimental result. So just using the correlation of the single point intensity with intensity detected by the camera here. So this is a single pixel intensity, and this is a array detection. If you are able to if you correlate, we are able to recover the two-dimensional object. So this kind of experiments, this strategy is very very much required, particularly for developing a single pixel imaging system, where you need only a single pixel detection, and with the correlation of another light, you can recover the two-dimensional object. However, in the previous case, we use the iteration method, because once you have the data, you have to take the data in your computer and then do the iteration process. So once you do the iteration, what you get, in certain cases it works, but if you have a very complicated object, there are certain limitations. So in order to overcome this issue, we developed another technique, what we call the interferometry in the intensity correlations, because you have seen earlier that intensity correlation gives the modulus square of W. Now, design your experiment in such a way that W is a function of two coherence functions. So rather than considering W as a just single quantity WO, what we consider, we devise experiment in such a way that W is composed of WO and WR, like a holography, taking the holography from the first order interferometer to the second order. Because in first order, if you remember, it was O and R. Here we are considering WO and WR. W is a coherence function. O and R, those two quantities were a complex field. So what we have done, we have brought the holography from the first order domain to the second order interferometric domain. And using this approach, once we have this kind of interference term, we were able to get the WO, because WR is known to us, because this is a reference coherence function. So this idea we applied to overcome the phase recovery problem in the ghost diffraction, because if in the previous case I told, in order to recover the phase, you have to do the iterations, and sometimes you may face the convergence problem in the iteration if your object is complicated. So in order to overcome that limitations, what we did, we relied on the holography of the coherence waves. So the basic principle of this this holographic ghost diffraction scheme is that we allow two coherence waves to interfere and then take the intensity correlation. So this is the approach. So this is a conventional ghost diffraction scheme, based on the Hanbury-Brown. Now, in order to overcome this limitation, what we allowed, because if you see here, in conventional ghost diffraction, the light from the classical or quantum, you take here light is being split into two parts. One part interacts with object and go to detector D1. Another which doesn't interact with object and go to detector D2 and then take the correlation, intensity correlation. Here, what we do before taking the intensity correlation, we allowed another third beam, which is free from, independent from the source, to reach both detectors, and then we measure the intensity from D1 and D2 and then correlate. Using this technique, so you see here, this is the inner part is conventional ghost diffraction scheme. We allowed this thermal light to split into two parts. This is a complex object, and this is the, so one light interacts with object, another doesn't interact, and then go to detector D1 and D2. Now, before detection D1 and D2, we allowed another beam, which is known because we need a known reference, and then light from this arm, it goes to detector to both parts, and then both are being interfered, and then you measure the intensity. Using this scheme, we were able to recover the complex field of the object, which is not possible in the ghost diffraction, conventional ghost diffraction, because we combined the holographic principle with a second order intensity interferometer, and that helps us to preserve the phase information in the ghost diffraction scheme. And we also applied this for the microscopy. So these are some results of our ghost diffraction. Now, we also try to replace this this laser source or with a thermal light source with a computational source. So what we call so here, rather than using the thermal light source, which is experimentally realized by using the rotating ground glass, you take the spatial light modulator, and which you create the randomness in the light, random pattern, and that random light will split into two parts, again following the same procedure like explained. Only the difference is that you replace the thermal light source with a digital laser, what I call the digital laser, because you are digitally controlling the randomness in the light. So using this principle, we demonstrated one technique, what we call the computational ghost imaging, using the single pixel detector. So the idea is that take the laser and using the rather than using the rotating ground glass to mimic the thermal light source, we use here a spatial light modulator, and this spatial light modulator displays the random pattern in a sequence. So the random pattern reflected from this introduced and then reflected from this device, spatial light modulator, will illuminate the object. And now this light from the object will be detected by a single pixel detector. It's just photodiode. Now this photodiode is fixed. Now what I have, whatever the pattern I am giving, I know what pattern I give. So I can digitally propagate this in my computer. So one part is your experiment, one part is your computational experiment. And then finally, because the data for each pattern you are measuring by photodiode intensity, and then you correlate this intensity, one from the optical setup, one from the computational experiment, and then you correlate. So the first part of the optical setup is following. So like random pattern you are giving, it's being this random pattern illuminates the object, and then you measure here at the single pixel detector. So entire light coming from this arm is just being integrated, and that's a bucket detection. So this intensity, modulus square of this quantity, will be correlated with the intensity of the light, which you are digitally propagating. And you may ask the question, how we can digitally propagate? Because the pattern which I am introducing in the SLM is in my computer. So the pattern which I introduce in my experiment, that pattern I also have in my computer. So I can digitally propagate. So each pattern I will allow to get inserted into the experiment. And also same pattern, I can digitally propagate. So I can digitally propagate here. And then I can correlate this intensity at different Z with the intensity detected by the bucket detector. And once we have this bucket intensity in two arms, if I correlate, 0 is here the bucket detector, because this bucket detector is fixed at the Z equal to 0 plane. On the other hand, the light which is coming from this arm, you are digitally scanning. This is the beauty of this experiment, because you are digitally scanning. There is no need to scan your single pixel detector. And then once you scan digital pattern with your single pixel intensity, you are able to get this complex this quantity, which will reconstruct the object. So once I correlate the digitally propagated intensity at minus 200 millimeter with a single pixel detector intensity, I get this object. When I go at the common plane, when both are in the 0 plane, means digitally detected intensity on this same plane, then I get this object. When I go to another plane, I get the reconstruction of the another letter. So this approach demonstrates that we are able to recover the 3D information with a digital illumination, or what you call the replacing the thermal light source with a digital source in the correlation holography. Now I will just in 2-3 slides, I will try to cover one of our recent works on the extending the second order interferometer to the polarization domain, particularly on the Stokes correlation. So the idea is this technique is utilized to develop a new holographic reconstruction method. So like I mentioned previously that if I have the randomness in the light, the first order interferometer will not work. So if I have the hologram which is embedded into randomness, I will get nothing. I will get only random pattern. In this slide, I am going to explain how we can reconstruct the hologram with a random pattern. Usually the randomness is considered a noise, and it's a problem in the conventional holography. But here, we want to utilize the randomness to develop a new kind of holography for different reasons. One reason is that to enhance the quality of reconstruction. Other reason is that to face the randomness in the path of the light and then overcome this challenge. So suppose this is your conventional hologram which you want to reconstruct. Now, if you reconstruct this hologram with a random light, you will get only random pattern, speckle pattern. Now, and conventional holography reconstruction will not work. However, what we have done, in this case, we have utilized this randomness and measured the correlation, 2-point Stokes correlation of this randomness to reconstruct the object. So let me see how it works. So the Stokes parameter is a kind of vector having a column vector having 4 elements, S0, S1, S2, and S3. So n goes from 0 to 3. Now, if you correlate this quantity, it will be 4 cross 4 matrix. Now, we have in our this particular technique, we have used only these two quantities, 2, 2, and 3, 2. Particularly, we have used these two terms to reconstruct the complex quantity encoded into this hologram. So the idea of this experiment is designed like this. Is the SLM displays the hologram or displays the target. That target goes to the random scattering media. And if you apply the conventional holography, because of this random scattering media, you'll get nothing. You'll get only random pattern. However, in order to demonstrate or propose a new holographic reconstruction technique, what we did, we allowed another beam to come from this arm, which introduces a randomness in this arm, and then light from this arm, means light from the hologram arm, random light from hologram arm, and random light from this reference arm. They interfere here. And then you measure the Stokes parameters. We measure the Stokes parameter S2 and S3 using the quarter wave plate and linear polarizer assembly. And then once we have S2 and S3, because we need correlation of S2 and S2 and correlation of S2 and S3. So once we have these quantities, we can get the correlation. So we got the S2 and S3 and then do the correlation. And once we have the correlation, we are able to recover the object which was encoded into the hologram. So even from your eyes, what you'll see only random pattern. But if you do the higher order correlation, extending the Henry-Brown-Twist approach to the Stokes correlation, we were able to recover the complex field. This amplitude and this is a phase. This amplitude of the number 2 and this is a phase. So we were able to recover amplitude and phase. So this is for the students. So this particularly the developing the higher order interferometry or higher order optics, higher order correlation optics with different sources, classical and quantum sources, are very emerging areas, particularly for sensing and imaging applications. Our interest is mainly in the imaging. So we are trying to utilize the different level of interferometry for various imaging applications. And some of our recent works are in the single pixel microscopy, randomness assisted imaging, and then developing the following the common link between classical quantum optics and developing some unconventional imaging techniques. So with this, I will conclude. So in this talk, I try to discuss the different kind of interferometers, and then what are the emerging interests in particular in this area, and then some of our recent contributions. So with this, I would like to acknowledge my students also from the IIT, previous student, particularly Dr. Binu, and other students, and also my present students from IIT BHU. And I would also like to acknowledge different funding agencies, CRB, CSIR, DVT, BRNS, and IDAPT Hub, IIT BHU. Thanks.